All right, so guys, we're gonna be using liquid nitrogen. That's why you all have goggles on. I don't want anybody to be hurt by liquid nitrogen. So I have a door behind me. A door is a device, container that allows you to store it. So what I'm going to do first is pour it in a smaller container just because it's easier to deal with. So now liquid nitrogen is extremely cold. Okay, so I'm going to pour some actually inside this beaker. And just right off the top, the first thing that you notice about it, is that it looks like it's doing what? It's boiling, right? And it is. It looks like it's boiling because it is boiling. Because liquid nitrogen's boiling point is minus 323 degrees Fahrenheit, which is way below the room temperature of room temperature. So it's all it can really do at this point is boil. And so you're right to be, concerned about the coldness. Now you're probably noticing that it doesn't look like it's vigorously boiling as much as it was before. And the reason for that is because the first time I poured it inside there, the temperature of the beaker was about room temperature. And what happens is when I pour the liquid nitrogen inside the beaker, it equilibrates with the temperature of the liquid nitrogen so that no more heat is flowing into the liquid nitrogen. Remember, if the beaker is warm and the liquid nitrogen is cold, heat's going to move from the beaker to the liquid nitrogen, right? And it's going to cause it to vaporize and boil a lot quicker. But now it's about equilibrated. But it's still very cold and really dangerous, right? But the interesting thing about it is that even though it's that cold, because of the Leidenfrost effect, you really can't, unless you kind of really trap it in your hand, there's really no danger of it, really damaging your skin or anything like that. Because anybody know what the Leidenfrost effect is? Yeah, what is it?
It's when something is the temperature between two objects is so high, generally with liquids and solids, that the liquid will turn to a gas and float on top of the hotter object. Pretty much, right? Because basically what it does is it creates a layer of air that causes it to kind of float above the surface of anything that it's on. It literally creates a layer of gas that just floats on, almost like a hovercraft or something like that. So I can just pour it on there, and it's really nothing. I can pour it in your hand. Anybody? Spread your fingers, though. Yeah. Yeah, it's nothing too serious, right?
But it's really cold?
Yeah, it's cold. It's cold. But like I said, it just runs right off your hand. I saw a guy throw it literally. If you wanna check this out, the guy's name is King of Random. I literally saw him throw it in his face.
I saw some guy dunk it.
So weird.
His whole hand in a bucket.
I don't know if we did or not, but yeah. So what I'm gonna do here is this is just a balloon filled with air, and I'm gonna pour some on the balloon just to show you what kind of happens here. So anybody predict what's gonna happen? It's gonna shrink, right? And that's because of something called Charles's law, right? And Charles's law says that the volume of a gas varies inversely with its temperature if you hold pressure constant. And I can literally just kind of put this inside here like that. I want to put that in there. By the way, step back a little bit if you're wearing open-toed shoes or anything like that. No, it's okay. I'm not worried about you in that sense. I'm just worried about it maybe landing on your feet or something. And I can literally just put a bunch of these in here actually because every time I pour the liquid nitrogen on there, the gas is just going to cause the liquid nitrogen is going to cause the gas to contract, right, as it should. And again, that's just a demonstration of Charles's law. And I could literally blow up all of these balloons that I have. I'm not going to, but I could fit 17 or 20 balloons inside there. And you're probably thinking, well, the balloon itself is just completely wrecked, right? But you'll see if I take it out, you'll see it just kind of reanimate itself because now the gas is expanding, it's heating up, right? and it'll go back to its previous state. So that's one of like the cool things to do with liquid nitrogen. We like to play around. You know, this is like the one job where we get to play with stuff, you know, and get paid for it. So I just need to heat this one. Well, this one actually popped, I think. Actually, maybe it didn't. It just needed a little more coaxing. So if I just kind of, and it's just, you know, it feels just like a rubber balloon. You know, it's nothing, you know, back to its original. One of the other things that we like to do, and somebody already saw this. I should have swept it up. We just like to put stuff in liquid nitrogen, and so I just put a little rose inside there. Now, anytime you put something in liquid nitrogen, usually makes it pretty brittle, and that's because the bonds normally, not bonds between solid molecules, usually have some sort of elasticity to it, meaning that not so rigid. But when you cool it down, the energy decreases and the bonds actually become more rigid to the point where, you know, becomes really brittle. And I want to let that sit in there for a while. I actually had something else planned. By the way, the door, you might notice that the thing I pulled out of the door is this thing. And this is not a top by any means. You literally are not allowed to transport liquid nitrogen with something that will seal. Can you guess why? Yes.
It'll explode.
Yeah, it can explode. Pressure can build inside of this container. And I have to drive, like I had to drive from New Jersey with this in the back of my car. If it exploded, if there were no shrapnel, right, because there'd be shrapnel everywhere if this thing exploded, but even if there weren't any shrapnel, the rapid increase in gas inside the cabin of my car would cause a tremendous compression on my body, literally. And the area susceptible to most compression, like my lungs, my eardrums, like I'd be completely like wiped out. The only thing that would save me is if the windows blew out, right? And that's probably what would happen. And I was worried about open. So, I mean, like, I could even, like, you know, do this kind of thing. Now, people do this kind of stuff with, like, you know, people pour, like, liquid nitrogen on different, like, culinary types of things. You can make, well, no, I don't plan on doing that. But you can make ice cream this way. If you take, like, ice cream or just cream and sugar and you just kind of, you know, pour liquid nitrogen inside there, literally can make ice cream in a really rapid way, by the way. I just want to show you, it's perfectly safe to eat.
Oh my god.
Perfectly safe. This is perfectly safe to eat. I'm sorry.
Are we allowed to eat? I want to eat one.
Can I eat?
I'm really hungry.
Yeah. Okay, that's a neat
I'm feeling ice cream.
Yeah, it's
Hard. Flavor with sugar.
mildly chilly. You can feel the nitrogen expanding.
Well, the nitrogen is pretty much gone. All it's doing is cooling up the air. These cookies have like little air pockets in them, right? Carbon dioxide, which is what helps it rise.
Can you eat another one? Wow.
Well, that happens. That happens sometimes. It does actually. That's what's happening right now.
It doesn't
Yeah.
They have like a candy bar in LA where like the candy is that cold, and then people just like
Really?
eat it.
Wait, it's got liquid nitrogen actually. Hold on, let me pour it out.
Oh, nice.
Pour it on the head. Pour balloons.
Oh, can I put like a couple in my mouth?
You can, yeah, sure.
You vape?
Just down the entire cup.
This is so fun. Okay. Way too long.
Are you a dragon?
He's literally a dragon.
Do you vape, fam?
Vape. Watch the liquid nitrogen behind you.
No, don't worry.
Yeah, watch. Okay, I think this is done. And I just want to show you, like, this is, I mean, it was like, you know, by the way, roses, plant cells have water in them, right? Because, you know, all plant cells, all living cells indeed have water in them. And water is one of the few things that as you heat them, cool them down, they actually expand. And that rapid expansion causes the actual, the structural integrity of the cell wall to be completely broken down.
Oh, heats up. Is it gonna be like? Is it gonna look like you ripped a flower?
It's going to look like that, what's on the floor. See, this is what I should have done, actually. I should have done it here rather than like doing it over there, because I can clean this up. But this is, I just want to do one more thing. Just one more thing. I don't know if I can. I don't know if I have everything that I need here. I need a test tube. Is there like a test tube? Oh, here. Okay. So I just want to do one more thing, guys.
Is there an Alyssa Mays?
There is.
Yeah, she's here. Sure. Oh, hi, Mr. Teasdale. Okay, bye.
Okay. Everything okay?
Mr. Teasdale got this.
Does he have my wallet?
What I'm gonna do, guys, is I want to just pipe some methane into the test tube, and I'm gonna pour some liquid nitrogen over the test tube. Right now, the methane, when it makes contact with the sides, the really cold sides of the test tube, the methane is going to want to condense to a liquid, right? Because that's what happens to gases when they cool down. They condense to liquids. And so what I'm going to try to do is make some liquid methane. Now, it does take a little while. It takes like a good 5 minutes or so to get enough for me to do anything with it. But, by the way, why does this happen? Like, why does it condense to a liquid while we're waiting? Anybody? Why does the gas condense to a liquid? On a molecular level, what do you think happens?
Contacts the side of the test tube
Mm-hmm.
because the test tube gets cold from the liquid nitrogen.
Right.
It condenses onto
But-
the side of it.
But why?
There's
Less
energy.
Less energy, right? And what happens is now methane has the structure, you guys remember, methane has the structure CH4. And you know that that molecule is completely non-polar. And non-polar molecules do attract each other, but weakly, right? Through what types of forces? London dispersion forces, right? But if you cool them down enough, if you decrease their kinetic energy enough, then the attractive forces will take hold. And they will attract each other, but they have to be slowed down tremendously. So that's what's happening here. And you can see in the bottom, there's already a little bit of liquid methane. I want a little bit more, right? So I want to get it to about, I guess maybe like 3 fingers, something like that. That's just going to take me a little while.
Is all the gas being trapped, or is it?
No, some of it's escaping a little bit, but notice I have the tube all the way down into the bottom, so that it's, you know, making contact immediately with the liquid nitrogen. I can help it by, you know, making sure it goes to the top. Like that. Now, my question to you, you can go welding supply companies. They carry it. Different places have it. By the way,
Can just any civilian get
pretty much, yeah, pretty much. If you know where to get it.
Oh my god.
You can get dry ice anywhere. You can get dry ice anywhere.
Okay, I'm almost there. Guys, my question is, what type of change is occurring when I condense the methane gas to liquid methane? What type of change is that?
Sublimation.
No, that's not sublimation.
Sublimation is solid to
Yeah.
gas.
It's what? Condensation. That's right. That's specifically what's happening. But what type of change? A phase change. Okay, give me a more general, even more than that. Is it chemical or physical?
Physical.
Definitely physical. And if it's physical, then the methane should have the same chemical and physical properties, or at least chemical properties, right, that it did in the liquid phase as it does in the gas phase, right? And one of the properties, I should say, that methane has is that it's flammable, right? So we want to see